Hi, what we're going to look at now are inputs. And there is an example for using the GPIO inputs. So these are the little on different cards, you have inputs on it. So there is an example in the ESP-IDF of how to use inputs, but they're what are called interrupt driven ones. And they use what's called an ISO, which is an interrupt service routine. Now, if that doesn't mean anything to you, well, then maybe the term event driven means something to you. If that doesn't mean anything to you, well, then all that is with your PC nowadays, when you move your mouse around or you click is an event. Something happens. So modern code tends to be based around the fact that you have some background tasks that you're doing and you wait for something to be ready. You wait for something else. Maybe another part of the code wants to tell you, hey, I've finished processing that, and that's an event. Back in the day, millions of years ago, when I was starting out, we tended to write code in a much more linear fashion. That you started at a line, you went down, you went down, you went down. You maybe branched off, did something, came back. You did something, did something, did something. You looped up, you did something, you did something, you did something. The problem with this, there's some advantages in that. Now, the reason we had to do that was obviously memory, everything else was limited. One of the big problems is though you're cycling through everything and there might be nothing happening, but you're still going along. And maybe something's happening now, but by the time you get down to that something happening now, it has stopped happening and you've missed it. And then you go along and then something happens here and then you miss it until you get down to it. So big problems with that. So there are many techniques, and one of the first ones that came along was interrupt service routines, and that was you start your code and you're going along and you have these special logic lines that when the event that they're attached to happens, your code suddenly jumps to this interrupt service routine and goes, oh, I gotta handle this, gotta handle this, gotta handle this. What it's akin to in real world scenarios, you're sitting in your house. People, for whatever reason on this planet that you're living in, don't knock at the door or the window when they arrive. They just stand at the window or the door and they wait for you to open it and look and see are they there. And then they say, hello, how are you? So if you were expecting visitors, or even if you weren't expecting visitors, you would periodically have to go out, open the door, see is there anyone there. Look out the window, is there anyone there? Look out the back door, is there anyone there? This is polling. So this is a non-interrupt driven system. An interrupt driven system will be then that you tell them, hey, when you're calling over, I'm going to be sitting inside watching YouTube, having a cup of tea, and what you need to do is knock on the window. So you just sit down, you ignore the doors and the windows, and then when someone arrives, they knock on the window. And you get up and you answer the window, or you answer the door, or whatever else. So this would be an interrupt service routine. You are servicing the interruption. Or it's an event, and you're handling the event. Slightly different terminology for different sort of environments, but it's the same thing. Now, you might say, well, that makes much more sense, and yes, it does. The big problem with interrupt service routines are, certainly in the older micros and some micros, not every input will generate a unique interrupt service routine. An input might generate one, and then you've got to ascertain which input it is. Plus, what happens when you've got multiple interrupts happening at the same time? Do you ignore the other ones? And if you don't ignore them, what happens to the one that you're currently doing? Well, you need to park that one, store all the information related to that, and then go on to the new interrupt service routine. But what if a higher priority one of them, for example, someone knocks at the door, the telephone rings. You say, well, okay, I'll be back to you in a second. I'm going to go off and answer the phone. You go in and you answer the phone. But while you're on the phone, then something more important happens. Like maybe, for example, an alarm for your heating system goes off, that the boiler is about to explode. You say to someone on the phone, I'll be back to you in a minute. And you go off and you stop the explosion. And in theory, you stop the explosion, you go back to the phone, you pick up the call, say, yeah, I'll continue your conversation, finish that conversation, you go out to the front door, and you say goodbye to that person or come in or whatever else. And that's fine. But there's only a finite amount of times you can do that because every time you have to store all that, you put it onto the stack and then you store more stuff in the stack and you store more stuff on the stack. And if that happens too much, well, then you start losing information. And in our analogy, that would be you forget about that there was someone at the door because you've lost all memory of that. And that can cause conflicts, can cause problems. So interrupts are great, but they should only be used for something that's really important that needs to stop the flow of code. And the free RTOS that is used by the ESP32 has a very handy way of doing that called virtual tasks. And what virtual tasks are, they let you assign essentially things to run. So the main code goes off and does stuff, and then you can do a polling routine on your inputs. So you can check to see what inputs are active and whatever else. And this piece of code now, which is the final bit of code for this session, we're going to start off with much easier, much lighter, and we're going to go through with some of the problems and how to solve them. And we'll get to this bit of code that's on the screen there now. And I'm just going to open up the monitor there. And sorry, I have to click in something. So what this is showing there, it's saying input 0 inactive. So I have the capability, I have told in this code, the number of inputs are 10. So there's 10 inputs, so we're monitoring 10 inputs. However, I haven't assigned them all to different pins in it, but it's designed, it's told, hey, you could have up to 10 inputs. And when I press the button, so I have on this LilyGo T3 display, I've used button, not button 0, but the button that is marked as, I think it's just called key. Yeah, so it's marked as key. So when I press key, I can let it go, and there you see it says active. So what has happened there is, even though I have pressed and let it go, it logged the fact that I had pressed it and then displayed it down here until such time as it displayed the event. Because otherwise, if I hadn't latched it, so that's called a latch. If I hadn't latched it, if I had just pressed it and let it go while it wasn't looking, well then the input would never have been seen as active. And so we would have missed it. But we're going to see that more. And what if I'm confusing with that, don't worry. As we're going through the code, we'll actually see why we've got to do that and how we've got to do that. Now, this is actually displaying the state, and it's set to every 5 seconds it updates it. And this is in the main code here. So it's basically displaying. So here's our main, the application main, and we're checking it here. And we're displaying every 5 seconds. So we display it, we pause 5 seconds, we display the next one. But even though the main application is paused for 5 seconds, normally this will be blocking in that nothing else happens. But obviously, if I click it within the 5 seconds, it's at active there. So it did detect it, even though the main code was blocked. And that's because we are using a task. And we are using this task manager that comes in the FreeRTOS. Now, this looks like there's an awful lot of stuff there. Believe me, there isn't. This is mostly for latching the inputs and doing stuff. We're going to build this up very slowly. There are only two what look like obscure bits of code here that you don't even have to remember them. You just make a note of it because it'll always be the same for any task we're going to create. And these are the important ones here. This one, X task create, and this handle thing here. So that's it, but that's going to change. That's not going to really change from task to task to tasks. And the tasks are so powerful that we can have multiple things all running what appears to be at the same time simultaneously. But by using the tasks, we will end up that it'll all be done. And the FreeRTOS that's on this will actually handle all that and the tasks running on that. Okay, so let's go backwards in time and let's start writing this code. Okay, so as future me said, we're going to do an example on polling. All this time travel is getting very confusing. So we have opened up our VS Visual Studio Code and we're ready to get started. So as I'm going through this, we're going to build the application up line by line. Forgive me if I start explaining stuff to people that know stuff. The whole purpose of this series of videos is to get people that extra step up away from Arduino to programming in more like what you program on other microcontrollers. And you might wonder why. And you go, oh, I don't need all that. And Arduino's great. Yeah, and Arduino is actually great for prototyping or for doing hobby stuff. But it's not suitable for professional development. And if you're going to program other microcontrollers like the Atmel or the PIC AV, or you're going to be in an IDE that's much more like this. And you're going to have to do this sort of stuff this way. It's just the way it is. Now, there's other advantages. We'll talk about them as we go along. But as I said earlier in another video, there's plenty of videos out there on Arduino. There's very few on using the ESP-IDF. The documentation, there is stuff in it, but it's hard to get through, and it can be off-putting. I'm trying to figure out stuff. So the whole purpose of these videos is to explain how you do stuff in the ESP-IDF. Okay, so we've got Visual Studio Code window open here. So what we need to do is we need to create a new project. So hit F1 and this opens up the command palette. Now on my one here it's at the top, and if it's not, you just start typing ESP-IDF new project and it'll filter the list for you. So we're going to hit this. Now the project name, well, it's going to be GPIO project and it's going to be on polling. So that's what we'll call it, GPIO polling. We happen to know the board is an S3 because we're going to be using the LilyGo one that we've done in the last few. There are two buttons down the front. We're going to use the button marked key. S3, and I happen to know that it's on COM7. Again, if you don't know these at the start, it doesn't matter, you can change them in the code. There's nothing that you have to do at the start. Well, the one thing you're not going to be, well, you can of course move the stuff around. But anyway, we're not going to be using any components, so we just hit choose template. And that brings up the next one. Now, if it's not on this one, extensions, which shows these three, it might be on ESP-IDF, which gives you all the examples. And down here, there are GPIO ones. Scroll down here and try and find them. I'm probably not able to find them now. There is somewhere here, a GPIO example. It's probably near the top. We scrolled past it. There it is. It's generic GPIO and a matrix keyboard. So these are interrupt-driven ones, and we want to do non-interrupt-driven ones. Sorry, where was that? Oh, yeah, new project. So scroll back up to the top, click extensions, and then we want to go template, which will create an empty template, and it'll show you the path here, and create project using template. Once it does that, it'll say, hey, do you want to open that in a new window? Okay, so we closed, and we can now close down the other one. We'll maximize it, and we are ready for road. So it will have populated down the bottom. It will have populated the COM port, the type of processor. The directory that it's going to be writing to will be our project directory. You can see it's there. This is the setup, the menu configuration. So obviously this S3, there's many different S3s and there's different parameters, there's different memory sites. So this is how we select the memory site. This cleans any project that we've already built, builds a new one. This one is the flash method. We're using USB. And this one is to flash the device. This is open the monitor, and this one does these three steps. It builds, flashes, and opens up the monitor. So it's no harm in running this one first in case we forget to do it later. So we hit that, and it can take a few seconds to open it up the first time because it's pulling in all these stuff here. Don't worry about those errors. Nothing to do with you, nothing to see here. And once this finishes, it will open up new page. Okay, so the things we know about the LilyGo S3, and this is for the LilyGo S3, and we got those in a previous video from the LilyGo website, and we need to change the type of SPI mode to QIO. It needs to be 8 megahertz. The flash size isn't 2 megahertz. There's 16 megs. Now it will run with 2 megs. It'll just think that LilyGo only has 2 megs. So 16. What's that there? No, don't. Couldn't be bothered. So we've changed QIO 16 meg. The other one that you can change is single factory app, no OTA. That leaves most of the memory available for the application. So that's fine. And the other important one to go down here is ESP32 specific, and this sets the CPO frequency. We'll set that to 240, and that's everything. The really important ones on this one is the flashing mode and the flash size. Hit save, and I would like a way that something will come up on the screen and say, yeah, save is done. This will change here to write a new one of these. As I said before, if you open these, that's all the parameters there, but you can't edit these. Well, you can, but when you hit a new build, it'll rewrite them, so there's no point in it. So we can close that down. We can actually close that down. So now we have our chip set up. So we can go into main, and here's our main application. And this is the entry point. So when our application starts, it's going to pop down to app main. You can see also it's created this standard library from C stdio.h. So it's including that. there are other files that we will need to include as we go along. You will probably find that there's certain ones that you nearly always include, so it can be quite handy in having them ready to go. Um, so it can be quite handy to have them ready to go. I've also included a list of things to do, which I want to put in my project here, little to-dos. Okay, so the header files that we need. Well, strings, we're going to be working with strings. And that's one thing. C doesn't come with any support out of the box for strings. So I'm going to copy these libraries in here that I always use. And they're good ones to start going. So this one here, strings lets us work with strings. FreeRTOS and FreeRTOS tasks are two that we're going to need because we're going to be using the RTOS. And RTOS stands for real-time operating system. And they're the ones we're going to be using. We're not at this moment in time, our first run through of this, of creating the GPIO. We don't need this. So, but we're going to put it in. We're going to be using it very shortly. Now we can write our GPIO code, and what we're going to have to do, right? So we've done our, it says we includes, we set up a logger, and this is for logging, the ESP logger one, and set up GPI, pull-ups, etc. We can do all that in this main.c, but that gets unwieldy and it can get messy. And if we want to recycle our GPIO, so this code that we write, and when you write something like something for servicing GPIOs, you should try and write it in such a way that you're going to be able to use it in your next project. I mean, unless you want to sit down for 20 minutes writing the same GPIO interface every time, that's fine. But most of us will try and recycle our code. We're very lazy that way. Love copy and paste. So it's probably no harm to set up our GPIO code in a separate H file or separate header file, and then we just call it from here. So we go set up, configure the GPIO. Off you go, start it. Don't tell me anymore. And we'll do that. Another thing that can be handy is you might be, for example, you might want to use your own stuff for errors, your own name, or not naming convention, but your own defines for different pieces of stuff. So you could create a global file as well that stuff that you're using all the way through it, the application uses the same. So that's another file that we may set up. We will probably set it up. For now, what we're going to do is we're going to create a file that is going to handle the actual GPIO. It's the bit of the code that's going to interface to the GPIO. So what we do is we come over here to main, and we go new file. And this is what we're going to call our GPIO file. And this is something that we potentially will be using across our code from going forward. So we call it GPIO polling. Polling. Yeah, GPIO polling. Well, I know that's fairly much the same name as our application, so we might change it. So GPIO, we'll just call it GPIO interface. And we'll call it .h. Okay, so now, and it's created and it's opened up that window. We haven't included it yet, so this code here knows absolutely nothing about this. Just because it's in the same directory doesn't mean anything. So we have to tell the main application, the main bit of code, that, hey, I want you to include, INCLUDE, let's spell it right, this new file that I've created called GPIO. And yeah, it's been IntelliSense there and saying, it's trying to help you out, GPIO interface. Now, when it comes to the GPIO interface, we're probably going to want to write stuff to the screen. In other words, this logging. We're probably going to want to use strings. We're probably going to want to use standard output. We will be wanting to have to do tasks, and we will want to do RTOS stuff. So we're going to need to probably include these files in our GPIO file, because in the standalone library here that we're going to create, we can't rely that it's going to inherit them from somewhere else. So we need to put them in here. Now, you might say, oh, this is very wasteful. I'm including it here, and I'm including it here. Well, no. What will happen is when the compiler and the linker and all that are doing their magic, it comes along here. And in this FreeRTOS, it will say at the start of it, there's the, and how I did that was I highlighted and I pressed F12. It says, if not defined, include task H. don't worry about that. It's just saying about submodules that haven't been loaded. So it said, if you haven't defined it, then define this. And then at the very, 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 very end of this is an endif. So this is telling it that if you've already found this file, if the author of the code has already included this file in some other header, don't bother re-including it. So it's going to, the first time it meets this, it's going to include FreeRTOS. Then when it loads this file and it comes down to here, it goes, aha, I've already included that. So there's no problem including the same file in multiple headers. But where it gets wasteful is if you put in a header file, like say for this log one, in even one file, and you don't use any of the functionality out of this, well, then you're loading that for a waste of time. Now, it's interesting. So the RTOS uses the if not define, which is probably one that you may have seen a lot of before. However, ESP-IDF will work with that, but they actually, in their source documentation, they actually recommend that you don't use that. You use a slightly different, more microcontrollery way. So what we need to do is, when this file here loads, GPIO interface, in case some other part of our code, we write code that uses it more than once, on our own header, we should always put that proviso to only include it once. As I said, you can use the if not defined, define, and then endif at the end, or you can use, I was going to sneeze, you can use a special keyword, pragma, once. And this tells it to only once include this block of code. Okay, so pragma once is less typing, and as I said in the documentation, the ESP-IDF documentation, and I'll just get that up on screen there. Bear with me. Okay, so this is the documents on Espressif, the designers of the chip's website, and it says header file guards. All public header faces should have a preprocessor guard. That's this thing that tells it only to include it once. And it says a pragma is preferred. And it says over the following pattern, which is the normal one, the conventional one. If not defined, define it, and the end if. Okay, this document also tries to give a code formatting. And the reason they're doing this is so that code I write, code that you write, code that someone else writes, if they're public libraries, they all look sort of the same. I wouldn't normally use this underscore between words. I prefer what's called camel case notation, which is where you'd go do capital O for one, capital T for thing, and then classes would start with a capital D. That's just the way I prefer it. But these things change over time. When I was in college, you were meant to put type definitions, unsigned 8-bit integer, all this sort of stuff before it. But times change. Anyway, so this is why I'm doing this underscore, because it's in their recommended way of doing it. They also recommended way you put braces and stuff on stuff. Anyway, we're getting away from the what we're meant to be doing. So I've used the pragma once, so this means it'll only be included once. So now when I call this here, if I have another library and another library is using or something else using GPIO, and we reference this header, it'll only ever get included once. Okay, well, we're a good few minutes into this and we haven't written any code yet. I do ramble too much. I am Irish after all. Okay, so we have our headers set up and we have our main application main. So this is where it starts, and we're going to tell it GPIO interface. So what we need to do is our GPIO knows nothing. So I'm going to pick up a different chip because it's not attached to the thing. These things here are very, very flexible. So there's a lot of inputs, and I'm going to throw them up on the screen there in a minute. Actually, I won't because we're going to probably too long on this. But there's a lot of inputs here, and nearly every single one of them can be configured as an input or an output, or an input and an output. And you do that for if you want to read back if your output has actually changed state. And as well as that, it tells the input what to do. Do you want to pull it up? Do you want to pull it down? And we'll have a look at that in a second. Actually, I'll just get that ready now, and we'll talk about that now. Okay, so this picture here is from the SparkFun website. And it shows what it's done. And look, it doesn't matter. This is an 80 mega 328. And the input here has been pulled up to 5 volts in this case. And this is what's called an external pull-up. So what that does is when there's no input here, when there's nothing happening here, this pulls it up here and it sees 5 volts. So this is a logic one. So this input is high. What we would then normally do is we would put a switch here and pull it low. So we pull it to 0 volts. And then when that happens is this part here is at 0 volts, so it grounds this line. So the input here then goes to 0. So you will nearly always see two things. The switches on micros are nearly always being pulled low to 0 volts. If you don't have this resistor here, and the circuitry here is if it's CMOS, which takes very little, hardly any current at all to trip it. What normally happens is this will act like an aerial, and it will what's called float high, so it'll actually go high. But in situations that's very bad, leaving your inputs flow high, they're slow and that shouldn't be done. So we normally put a pull-up resistor, and you can see on this one here, this resistor is outside. What is very handy about these boards, the ESP32s, are they have these pull-up resistors, but on the inside of the chip. They also have pull-down resistors, and that's just that the resistor is pulling it down to 0 volts, and then you'd switch your switch to the 3.3. Generally speaking, you're going to be using a pull-up resistor on an input. That means, though, that when someone presses the button, if it's a push-to-make switch, which it generally will be, all these ones are push to make. In other words, when you press it, it makes the contact. It puts 0 volts on the output and the input. So when the button is not pressed, it gets pulled up to logic 1, and when the button is pressed, it actually goes to logic 0. Another way of referring to this is active low. That when it's active, it's low. So it's a bit counterintuitive. So what we're going to need to do is we're going to need to put pull-up resistors on this device. We also have to tell it what pin we want to look at. So we need to do that. So what we're going to do in our GPIO interface, we're going to have a little code block called initialize or setup or configure, whatever you want to call it. We'll say config. So configure GPIO. And of course, we're going to have to say if it's returning something, so it's void, we're not sending anything back to the main application, and we're not taking any parameters in. We're just going to go with it like that. And if I save that there now, this means this function here will now be available out here because we've included this file. So if I invoke it, all I have to do is remember the name, and a handy thing here, we can split the screen here, and I can see it's opened in this one. Sorry, yeah, this is in main and this is this one. And the first thing we can do is we can say let's configure our GPIO. And hey, why not? We'll do that in a second. I was going to say let's put something on the screen. So what we want to do is we want to config underscore GPIO. And that's all we have to do. We're not passing in any parameters. So when the main code starts, it goes into here, calls this, and this will configure our GPIO there. Now, this is perfectly fine. It will come in here and it will find this function, and we're not calling anything else. But I want to come back to this in a minute because there's a slightly something else we should do, but we'll leave it fail. We'll leave it have a problem later on in our code, and we'll come back and we'll address this. So in our config GPIO, we're going to do that. So let's start outputting stuff to the screen. So the stuff we want to put in. So it's very important that you're telling, especially when you're prototyping this, that what's going on. So we go ESP log I for information. This is a built-in command because we've included this file, this library here, and it is asking for two parameters: tag format, well, up to minimum of 2 parameters. So the first one is tag, and all tag is tag. I'm going to make this available to all of this file, but this file only. So we say static, it's constant, it's not changing, and that's better for memory. And it's going to be character array, and it's going to be, we're going to call it tag, and we're going to equal that to, and we're going to tell it, so this is going to preface any output we put as something. So we'll say in main code. So we're in main code, so it's going to put that. So we say ESP log, and we go tag, and the message we want to put. We're going to say about to create our GPIO. So it's going to dump this to the screen, it's going to jump here, and it's going to go there. Let's compile this and make sure we've no silly little errors. The first time we compile this, it's going to take a while because it has to build everything from scratch. So I'm going to pause it and we'll come back then. And yeah, it did fail because I don't know how it happened, but this ended up being orphaned up here. I don't know how on earth that happened or when that happened. I suppose I can look back at the video and see when I did that. Must obviously typed something in there. No, it's doing. I see what's after happening. I use a thing called Prettier, which sort of fancies this all up, but it actually can be handy at time because it's done this. You saw when I moved it down, and it's because I've forgotten the semicolons up here. School by error. Now, if I save that, it'll actually save it better. So that's why I failed on the compile. So let's hit the compile and the build, and it should build much quicker this time because it's only that one little error that it's missing. Okay, so we got it nearly straight away, and once you get this with stack size and all this, you know your job's up. So right, so the code's going to come in here. It's going to print this out to the screen. It's going to call this function, which is in a GPIO interface, because we've included GPIO interface, and it's going to do absolutely nothing. So why not let's log from here. Let's log something, because we've included the log here. So let's say static constant. So static means it's only available to this file. So it's like private. It's a character. It's a pointer con. We can't call this one tag because we've got tag already. So tag, and we'll call it tag GPIO. And it's equal to, we'll say, in GPIO library. Semicolons. And then when we get to here, we'll go, we'll dump something to the screen. ESP log information. We'll go tag, and the tag is tag GPIO. It's prompting us for it, and format. And what's our little message? We're going about to set up a pin, a GPIO pin. And what I'm going to do is I'm actually going to download that to the device and run it. So we know it'll probably compile, my famous last word. So I'm going to be cocky, and I'm going to hit the build flash monitor. So hopefully I haven't got any little errors in the meantime in there since I fixed the last one. So there it goes. Yeah, it's happy with it. It's going to start. Oh, so I haven't flashed anything to this yet. So up the top of the screen here, it's saying, hey, how do you want, you never told me how you wanted to flash this. Well, we're going to use UART. We're going to save that there, and it's going to connect. It's going to flash that down. It's very small. And it's going to reboot it, and it's going to open up terminal. Well, now all that green stuff. So all that green stuff is the information stuff, and you can see here the yellow stuff. So it's doing a lot of boot stuff. Now you can switch all this boot stuff off. It's telling you about the heap and stacks and everything else. So CPU start schedule. So here's our first one. Here was our in main code, which was this one. So came down here, about to create our GPIO. So did that, called this, straight away down here, it jumped to here and logged us about to set up a GPIO pin. So at least we know the code is flowing the way it's meant to flow, which is always a good thing to know. So now we need to actually set up the GPIO. So we've called this function here configure GPIO, but we haven't actually configured any GPIO. So what we must need to do first is, so we need to set up our pull up resistor, and we need to know what pin we're on. So we haven't talked about that. What pin are we on? Well, to be honest, the documentation for the LilyGo doesn't say anything about pins. So I have managed to find it out through having a look at the other files. And what I mean by those other files are, so this is the files that we downloaded for the factory example. If we go into our factory example here and we look at the code, we'll see. So here are all the files and all it includes. There's one called pinconfig.h. If we open that up in Notepad, and just bring Notepad over here. If we open that up in Notepad, then we can see here is the Wi-Fi passwords and all stuff like that. But here is the ones for the LCD. And if we scroll down here, here's pin power on and pin button 1 and pin button 2. And pin button 2 is the one that's labeled key. So it says it's input 14. So button 2 is 14. And you can see here that the battery voltage is connected to pin 4. So that means, now that's an analog input, but if we actually have a battery, we can read the battery voltage. And maybe that's what we'll do, if I remember, is to do an analog input in the next video, and we can use this battery voltage. But this is, obviously this is only for this board. Other boards are different. Other boards are better, that they actually, like the SparkFun or the AllMX ones, actually give you the circuit diagrams, so you can see what is wired to what. You can see, oh, that LED is on, whatever. So that's handier. So this one doesn't. Or maybe I'm doing them wrong. Maybe I just didn't find the circuit diagram. So anyway, it's 14 is our pin that we want. So that's our output that the button's connected to. There's nothing stopping us connecting it to one of these other IOs up here, but let's use the one that's on it. So what are we going to call that button? So we need to define that pin somewhere. We can use the number 14, and let's do that first and talk about why that's a bad thing to do. So what we want to do is we want to set up our button. Now there's two ways we can do this. We can create a structure and then use that, and I'm going to show you both. And there's different reasons why you do different ones. The easiest way, and this is the way you would do it if you're only worried about doing one input. Is a command, and the command comes from this. I'm just going to throw up this website here. Oh, that's the wrong one. My apologies. My apologies. That's about task creation. Just get the right website there. GPIO. That's the one I wanted. Actually, open a new window because that one will be handy. Come back to that. So this is from the expressive one. So this lists all about the GPIO pins and the different functions that come as part of the GPIO library. I said, what GPIO library? Yeah. So we need to include a GPIO library so that we can use these GPIO functions. So we do that in our include up here. So there we go. GPIO control, it's called. GPIO_control. Now I am absolutely lying to you. It's not called that at all. It's called, senior moment there. Okay, so driver_GPIO.h. The reason I gave the squiggly line is it knew I hadn't a clue what I was talking about. So if we include this header file here, we now have access to all these functions. And this is what I mean. It's unwieldy. Configure GPIO such as output only, input output, and it doesn't really tell you much more about that. So that's the reason I'm doing these videos on the ESP-IDF. To talk about that. So this gives us the GPIO functionality. So what we now need to do is we need to configure the direction, whether it's an input or an output, and we need to then say whether it has a resistor or not. So the command is GPIO set direction. And how did I find that out? Well, I found that out because I went through these files here, and I found one of these was GPIO. There's GPIO pull up enable, and one was set direction. So GPIO set direction, and it's going to say, well, hang on a second now, I want the GPIO number and then the mode. So the GPIO number is the pin, and it was number 14. And we want to go what the direction is. And they have defined some words already. So we can use GPIO mode output, or input even. So GPIO mode input. So we're now saying pin 14, GPIO pin 14 is to be set as an input. And there's people hopefully screaming at the monitor going, what are you doing? You can't do, that's awful, that's terrible practice what you're doing. And yes, it is. So I'm just going to do this. So we want to set the pull up, and we want to set an internal pull up resistor. And you can see there's one of the prompts there is pull mode. So we're going to set the pull up to, guess what? Well, we have to tell it. So we're going to set the pull mode, and it's saying what GPIO. So it's 14, and what type of way we want to pull it up. And our options are GPIO, and our pull, down disabled, down enabled, pull up, down only, pull up disabled, pull up enabled, pull up only. So we're going to do pull up enabled is what we're going to do. So this is the one we want. And we want to put our semicolons at the end of that. Now that will configure input 14 for as an input, and it will enable the pull up resistor. And why I said, so hopefully this has riled you up, and I'm going to sort it. If it hasn't, then please learn that it should do. We should never refer to the number, we should never put these magic numbers in here, because we may change a different board, and then you've got to go through every line of code that uses this 14, and you've got to change it, and chances are you're going to miss it. So you should do this as a define. So we should do a define up here just after our includes, and we should say define, and we will say input button, and it's called key on this, so we'll call it there, input button key. Now, one thing you don't do, you think you would do an equals here, but when you're using a define, you give the name you're defining, and you give 14, and you just no semicolons either. So these are called preprocessor tasks, and all it does is it replaces anywhere it finds, it's like a control replace, anywhere it finds input button key with 14. You'll never see that. This is different from the compiler, so to replace these. But the advantage of this is now, if we go to a different board and we decide to want to wire up a different pin, then we just change it at the top here. This was similar to what these have done here. They've grouped up all their pins and they put it in a separate header file. So if you need to change any of your pins, you just change there and it will change in our code. I like to put what's called sometimes a file called global, and I'll add that as an include, and everything that's global to the whole project I'll just throw in there so that I'll remember where they are. So this is now set this as this device here button as input enabled, as an input, and input enabled. Let's make sure we've no little errors, and we'll hit, because we'll hit compile, and hopefully that should compile away. If it doesn't, it's no big drama. So now when we configure here, it comes to here, configure GPIO. So the GPIO is ready to go. And it's a public function because we're invoking this from outside of here, so we don't use the word static. So next thing to do, well, that's great. We've configured the GPIO and we've set up the GPIO, and now we need a way to read the GPIO. So let's create another function that will read the GPIO. And it will read the GPIO of the button that we want to include, or that we pass it, and it will then give us the value back of whether it's a 1 or it's a pass or a pass or a fail. It's an active or an inactive. So we're going to be passing back. It's an integer. How do I know it's an integer? Because the file, the header, the information, the document on it states that it's an integer, and the command we want to get to read it is sorry, I'm just looking for it there in my notes, and it is I can't find this. Get up state. So the method for getting it back is this command here. It's GPIO get level. We pass in the pin we want to, and it will return an integer. And it says if the pad is not configured for input or input and output, the return value is always 0. And it gives a little example. Okay, so that's what we want to do. So it is GPIO get level. So I'll copy that there, and it's going to return an integer. So what we are going to do is we're going to call it here, and we're going to pass it back up to here. Sorry, I'm just thinking, no, what we'll do is we will call it there. So it's going to be a public one, and we're going to actually display the value here. So we'll call this read input. And what we're going to do is we're going to need to know Okay, yeah, let's just keep this easy for now. We're just going to read just the input that's there. So we're going to read the input. No, we're actually going to pass it back. Sorry for all this fuddling around. So we're going to go integer, and we're going to go read input, and we're going to need to pass in a value of what input we want. So it's int input to read. So out here, after we configure the GPIO, we're going to need a way of reading this input. So we're going to do read input. I spelled it wrong. Read input, and we want to read, well, what pin do we want to read? Well, we want to read this input button key 14. Input button key. Now this knows what this defined as, even though this is in a file. So this, we've defined that in this file up here. It is public, it's available for everyone, and because we've included this file here, the compiler will understand this. So we say read input that. So that's just going to read it. It's not going to do anything else. So it's going to read it, and it's, so let's read the input. So to read the input, all we have to do is so we're going to return the value of GPIO get plus get level. It's prompting us for that, and it's going to be input to read. This may give a little error because I'm passing in an integer, but this is actually wants a slightly different type. We'll see. It may or may not give us an error. So what we're doing is here, we're telling it to execute this function. This will read the value of this pin here that we've passed in, and it will return it back up to here. Now it returns it to here, but as you can see here, we're not doing anything with it. So we should give. So we'll call it logic is equal to. So now when it comes down to here, it creates a variable called logic is and assigns the return value of this function to it. So it's going to come down here, it's going to execute this, it's going to read from the microcontroller what that input is, and it's going to send it back up here. And now let's print that to the screen. So we'll go ESP log I, and it's going to be tag, because we're in the main one, and it's going to be we know it's key is. Now we haven't talked about how do we pass back variables back to the log. Well, this is a very C thing. So it's an integer, so we go %d, think of for decimal, and then outside brackets we actually put, and if you notice here it's changed to vargs, we put as many of them as there are. So there is only one, so in this case it's logic is. So that's going to return that back up. Let's compile that. We may get a little error here, we might get a warning, and we might get away with it. Let's have a look, because it's not actually an integer. No, it's quite happy with that. So let's run this code here and see how useless it sort of is. So there it is. It has flashed. It's flashing it there, and it's going to start, and it's going to do that. And basically, if I press the button, nothing is going to happen. So I'm going to make sure I press the correct one. Oh shit! Sorry. What happened there is I hit the reset. These devices, that's a silly place for that. So and these have an awful. Once you do that with it, they go really screwy. You have to hold the button down and press reset to get them back. It's just there. Yeah, and this is going to be permission denied. 2 seconds here. We'll just get this. Okay, so it's back. So all that's happening is I'm going to try not to hit off the reset button this time as I press it. When I press the button, nothing else happens. Okay, So nothing else happens as I press the button. And so it's only read it once, and it says key is 1. And remember, 1 is the inactive state. So what's after happening here? And the reason that's after happening here is we've done our configuration, and then we've said read the logic and output it. But we've only done it once. So it's just going to go and it's going to end. So it's going to read it once and it's going to end. So what we need to do is we need to have what's called an event loop in this main here. So something that's run. So we would normally set it all up, and we go, now that the config is done, create an events loop. And what we will do is we will go, there's several ways of doing this. People prefer different ways. Some people put it into an endless loop, which would be for, this is the way ESP seems to do it a lot of times. So essentially this is a for loop that has no parameters, that never ends. So that's one way of doing it. That works fine. Or another way to do that is to do a while loop, and you go while 1. In other words, while it's always true. So the documentation seems to favor doing it this way. So this is a for loop that runs forever and ever and ever. So now what's going to happen is it's going to come in here, it's going to do this, and it's going to loop back. Now that's going to go crazy. It's going to go ridiculously fast, because it's going to, as soon as it does this, it's going to jump back here and do it again, and do it again, and do it again. So we should really put in a delay. And how we do delays, in Arduino land, there is a delay command, and how we do in FreeRTOS is slightly different. So we go vTask delay, and now we put in a value, and we'll say, for example, 200. So, but what is that? 200 chickens per square foot? What is it? Well, we need to tell it that we want to use, so the magic command is we go port tick rate, tick period, milliseconds. And so we're telling it basically 200 milliseconds pause. So it comes down to here and it pauses, and then it goes up and reads it again. And we will build Flash and run this again. So what we should now see is our input should constantly be saying input is 1 until such time as we press the button. And you can guess where I'm going with this. This is not a great way of doing things. And we'll see why once it works. So it's saying input key is 000. Yeah, that is obviously not right, because the key is not 0. So we've done something wrong here, because I've done something wrong here, because that should be showing 1. It should be getting pulled up high. So let's have a look to see what the problem is with that. I'll just get rid of this out of the way. Okay, so a little interesting bug there. When I run it, the very first one it gives is the correct one, but it's giving me an incorrect value. And the reason for that is down to the fact that I have actually used the wrong thing here. So this is the wrong parameter I've passed it. So I've told it to GPIO pull up enable, but that's not what should be passed. If we go back to this setup mode, set pull mode, and we look at the options for GPIO pull mode and click on that there, our options are pull up only, pull down only, pull up, pull down, which is both of them, and GPIO floating. So this is the one I should have used. And this is a number. So when it gets passed in, I passed in the wrong thing and got erratic behavior. That's why it's always good to post that in, stick that in there, pull up only. And now when I compile it, it should work fine. So it's good to act different, if you can test as you go, do test and go. And we're expecting ones. We're expecting ones all the time until I press the button, because they're active low. So now we can see it's 1, and I press the button. Oh, I pressed the wrong button. That's the reason for that. I press, there we go, zeros as I press, and ones there when I let go. So zeros and 1, 0 and 1. Now, I've said this is a bad idea, and I'll show you why this is a bad idea, the way we've done it. So we're coming into the main here, and then we'll forever loop through here. That's fine. That's an event loop. That's going to run forever. As long as our micro running, this is going to run, and that is absolutely no issue with that. And it reads the logic, passes in a value, reads the logic here, and pumps it out here, prints it out here. If we did other things, we could pass it to them and get them to do stuff, and that's perfectly fine. And we've got a delay here. This is our problem. This is what's called a blocking delay. Let me put that up to 5,000. In other words, 5,000 milliseconds, 5 seconds. Save that, and let's flash that to our device. Look at all these old tasks. I'll just kill them all off there. Okay, and now it says 1, and it's stopped, and it's going to wait 5 seconds, and it says 1. And it's called a blocking task because it blocks the whole main code of operating. And I press 1 in between there. It doesn't read it, it doesn't do anything. The ESP, for all intents and purposes, has stopped here when it's got to this loop here. So this is really, really bad. And what we should really do is we need a better way of doing that. We should leave this free run to do other stuff. So this should be going off and then periodically calling this. And that's our next stop there. And just to prove that this is this, what else? I'm going to put in here. Going to sleep. So it's going to say going to sleep, and then it's going to come back up here and do that. And you'll see that that is, we'll just close all these old ones down, and we'll flash that. So it says key is 1, going to sleep. So what we should really be doing is we should really be doing, and I'll close this down there. We should really be doing our sleeping over here. So let's do that. Copy that out of there. So now we pull it. So we should be doing all this over in our inputs. So we should be doing our looping here on our inputs. So what we need to do is we need to set up a loop here. So let's set up, and we go like this, we'll do this, and we go, and oh no, that's not going to work, because if we do our forever loop here, then the code is never going to leave this block here. It's going to come here and run here forever. What we want is a method here where we can start our application and then get it to do something else. And that's where virtual tasks, our vTasks, come along. Because what we'll do is we will create our input, this thing here, read input as a task. And the real-time operating system will go and do all that. And then we don't need to have our, well, we can have a for loop here, but we don't have to be keep on looping and checking the logic here. So let's have a look at doing that. Okay, so let's just clear up all this here for the moment. Go back to there. So really, when we configure our GPIO, we want to have our task over here just running. So let's just get rid of that there for a second. Let's clean all this up to make it a little bit more visible what we're going to do. So when we come down to here, we're going to configure GPIO. We get to here, we've configured all this, and now what we're going to do is, so we've done our includes, we've set up our logger, we've set up our GPIOs, and now the last thing we're going to do on this one is set up GPIO task. So the GPIO task looks really weird and exotic as we're doing it, but they all tasks, all in this follow the exact same structure. So what we need to do is we need to, first of all, we need to create a thing called a task handler. But before we do that, let's just give ourselves a little bit of a set up the free running GPIO task to read inputs forever. Right. So let's give a little bit of a shout out to the crowd. That's what we're doing. So we're going to pump this out. We're going to say setting up the GPIO task. Right, so that's that task. So, wow, that was on. So the first thing we have to do is we have to create a thing called a task handle. And task handle. So we're going to create a data type called task handle. So the data type is it's called task handle, and we're going to create a handle. I'm going to give it a name. Any name we can call it, Jeffrey, if we want to. We're going to call it X handle. And we're going to set it to null, meaning it's not set. It's not set. This value is not set. It's empty. And where am I coming up with this stuff? Well, this stuff comes from when I opened up here earlier, and this is the FreeRTOS, and this is the XTask create, and it tells you here this is what you have to create, this is what you need. So this is the FreeRTOS operating system. So we see we've created this handle. It's a data type handle, and this is just like an integer or a floating point number. So it's a data type called a task handle T, and here's the handle. So this is just the name. That's why it's in white here. Now this keyword static, when you use static outside of a function, it means that essentially makes that whatever it is private and only accessible by this. Whereas when you create it inside it, it means retain the value inside this loop. Now we're no longer going to be reading the input from here. So we're not going to read the input from here. So we're going to read it from out here. So this is going to be private functions. And this will be our public functions up here. And how do we make it private? And you should always make functions private so that you can't accidentally call and overwrite values. We use the word static. So now if we try and access this from here, and we don't want to return any data, so we go void, and that means we can't use the command here. So we're going to deal with that in a sec. So we're going to give a value. So when we get a value, call this logic value. Equals to that. Okay, so now we're going to read this value here. We're not doing anything with it. We haven't saved it. We haven't written it to the screen. So what we're going to do is we're going to if logic value is equal to 1. Now remember, 1 is inactive. We're going to say ESP log to the screen information, and it's called tag GPIO. We're going to say the word inactive. Otherwise, if it's not, we're going to log to the screen the word active. So now we're going to read the input, and we're going to say it's either active or it's inactive. Right, so this is the task. This is what's going to be periodically run. So we're going to create the task up here. So setting up the GPI task, the first thing we do is we create this thing called a static task handle. And we set that to null, to nothing. Now what we do is we must create the task. So that is this thing here, XTask create. So we go XTask create. And we pass in several things to it. So the first thing it says task function, a pointer to the task code. Okay, this is very, all this means is the function we want to call when this task is created. So this task is going to run periodically, or it's going to run. So we're going to call input. So this is the task we're telling it. Read task, read input. So this is the name. The first variable it gets is the name of the function it's called. The next thing it says is PC name. So this is the task name. And this is something that we can put in ourselves. So we can call it poll GPIO. Okay, so that's its name. The next thing it wants stack des. I'm going to put in 2048. Why? Well, we'll talk about that in a second. The next thing it wants is, do we want to pass in any parameters? And do we want to pass in any parameters? Well, we're actually not going to be passing in any parameters, but it's no harm to create a variable for that. So we will, and I'll show you what we'll do. So it's asking for this PV parameters. I'm actually going to do that now. So we're going to do that now, and up here in our private member variables, we've already created this one here. We're going to create this one static, and it is unsigned int 8-bit type. Just have to call it, and we give it the name UC. We call it parametered pass. So UC param. We're just going to call it task. Okay, so we're creating this, and we're not actually going to be using this in this one, but we still need to pass in the name. So we're down here, so we're going to give it in task param. Sorry, not task comma. Right, task parameter. The next thing it wants is the priority. And this is the priority of the task. So that if another task is doing something, does it override it? Does it do it? Is it allowed to be delayed or anything like that? So we'll give it priority. Sorry, in this case, it's actually what core it's running on. So we're going to tell it to run on core 1. And we are then going to, the last thing we must pass in is pointer it's asking for. So let's just see that again. So it's a constant pointer for created task. So we need to give it a pointer. And that's why we created this thing xhandle here. So xhandle is created. We need to give it the memory location where that lives. So we go the address of xhandle. Now this looks very, very spelling it wrong. Here's of course case sensitive. This looks very, very convoluted, doesn't it? But this is the way you always create tasks. And once it becomes second nature, they'll all follow the exact same format here. So what we're doing is we're creating this thing called a task handle xhandle. We're setting it to null. We'll then create a function. We tell the task that you are to run this function here. So read input. We then give it a name. We then give it a stack size. This is how much memory we want to allocate to that. And again, I don't like doing those, so I'm going to make a definition up here. And I'm going to call it default stack size 2048. 2048 is a good place to start with a stack size. If you start with stack size too small, then what will happen is it could cause the program to crash because it doesn't have enough memory. There is a technique you can in the code. Once it starts, you can see how much memory it's using and then adjust this down. We are giving it, we're saying if we want to pass in any parameters. So if we were giving this different inputs to read or whatever from outside of here, we can pass them in via this task parameter. We're not going to be doing it, so these aren't set. We're just going to leave it there. You do have to pass in a variable here. The next thing is the priority, and then this pointer that we've created here. And the reason we create this here and we pass it in here is when the task, if the task is not created, then the value xhandle will still be null. So it will not have changed. So let's output this. We need to warn our code at the start. Actually, and do you know what? I'm going to put that in as a log D for debug because this is a major issue. And actually, no, we'll just keep it as a yeah, we'll put it in as a debug. I know, you know what? I'm going to confuse myself there later on. So we go tag GPIO, and we're going to go warning failed to create GPIO task. Otherwise, the task has been created. Now, if it has failed to create it, what we should do is we should invoke vTask delete, and we give it in the example. Okay. No, Jesus Christ. Right, I'm getting tired. That's the problem now. Okay, so now if it's all gone through here, it will create this task, and this task will run. Now, all we're doing here, though, is again, it's only going to run once. So it's going to come down here, and it's going to run this task. But we haven't stuck this in the loop forever. So we need to put this in a for loop. And do that. And that's going to run forever. Now, we want to put in our little delay. We want to give this a delay. So how much of a delay we want to go is, let's create a define up here. Delay, we call it GPIO delay milliseconds, and we'll set it to 100. So it's going to wait 100 milliseconds before each time it reads these. So that's going to be quite fast. So here's our for loop. That's the braces for that. If we hit save, it'll indent there. And we want to put in here, we want to go vTask delay, and we say whatever we call that there, GPIO delay, copy that. And we divide it by the port tick period milliseconds. Now what's going to happen is this task is going to set up. So this is going to create our task. It's going to check that the task was created, and it's going to run that task. This task will loop forever. And let's just see, does that all work? No, okay. So we have some errors there, and let's go, and it said, oh, yeah. No, that's okay. Read input, static void, read input. Why does it not like that? Because it is static, it should be static. Read input. What's it saying? Access, undefined first use. Oh, okay. Yeah. So now, if you remember, I said we'll go ahead with creating the functions, but there is a bit of a problem the way we're doing it. We're just creating our function here. What's happening is, as it's compiling, it's coming along here. It's saying I have to include this, and so the first thing it does here is it includes this GPIO interface, and then it works through here and it sees the word config GPIO, and because this include was prior to this, the config, it knew what GPIO was. It comes along here and it goes, hey, read input. What on earth is that? It doesn't spot that down here there's a read input. So you need to have your function all nicely done before it gets to this point. So there's one way of doing that, which is not the best way, is to put this up here. And now when I compile this, it'll be able to, because what's after going to happen? Okay, I've got another. No, it's fine. Okay, because yeah, it's happy with that. That was that one that didn't, whatever. So now what's after happening is it comes along here, it sees the definition here, it goes, yeah, that's great, I don't know what it is. So when it gets down to here, it knows what read input is. Now we end up with a situation, if I had a function here, then I'd have to make sure this one is called before this one. And that's just getting very confusing. So I'm going to undo that. And that's of course going to give us our error, because now it's talking about this read input here, and it doesn't know anything about read input. So what we can tell it is, at the start here, we can go private functions, private methods, and public methods. And what we do is we tell it, hey, look, don't get into a heap. I know you're going to be looking for this function here called read input. I know you don't know anything about it, but what I promise you will be defined later on. So we can put this up here. This is a private one. We put this up here just as if it was going to have, it's just the name of it, and we put a semicolons after it. So now it's promising it that here you go, here's a read function. I'm not defining it here. I'm just saying it exists. And then when it comes to here, it goes, okay, this exists somewhere, and then it links it back to there. So now when I compile that, it should be happy, and it should compile that up. Now it's finding them, it's saying, oh, warning, I might be able to find them, and yeah, it's quite happy now. So what you should always do is, in the start of your header file, you should give the names of the functions you're calling. So here we have this one, so that's read input. So again, this is private, which is the one I've just done there. This one here is public. So in our public section up here, we should give this here. Again, just the semicolons after it. So now when it's coming to the compile here, it's going to know that this exists. Should always do this. So this is our private functions, our public functions, our private member variables, and then the actual functions themselves, and the private functions. And that way, by naming these up here, you're not going to get any of these weird compile errors. Let's run that. So that should run now. Now it's going to be quite fast because it's 100 milliseconds. So it's saying inactive, 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 active, 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 inactive, 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 active, active, active. Okay, so what you might say is, well, that was an awful lot of work for nothing extra. I can see where you're going with that, but let's have a look at what's happening. So now we have our main application here, and hang on a second, we've no loop here. So what's happening is, this is actually just going config and it's doing nothing else. How's that happening? Well, when we go to config GPIO, it runs this public function. It creates this here task. And this task will run forever in a for loop, its own little events loop. And the advantage of this is, it means this can run off in a different core. We can actually do stuff here, over here in main, and we can have this doing something completely different. And it can go off and do other stuff. So for example, let's go back to and create our main events loop. And let's go forever. And we are going to have a loop that runs forever. We're going to dump out the word message. Let's tag. I'm going to say main event loop is going to sleep. And then what we're going to do is we're going to do a delay. And we're going to delay for, how long? 5 seconds, like we did before. And then we're going to go I'm awake. And then it's going to go back to sleep. So now we're going to have a loop, a blocking loop for 5 seconds. The last time we did that, nothing else happened. So let's have a look at this. And what do you think is going to happen? So let's have a look at here. It's saying here's it's coming along here, and it's saying main event loop is going to sleep. So the main event loop, this up here, has gone to sleep and is going to go to sleep for 5 seconds. But that doesn't stop this task here from running. So this bit of code here is still running away, chugging along every 100 milliseconds. And then bang, look, timestamp 5306 in main code, main event loop is awake. Main event, so then it jumps back up here and it goes main event is going to sleep. So this loop here goes to sleep. And 5306, it's gone to sleep. And then we're going inactive, inactive, inactive. inactive, 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 and then, oh look, 5 seconds later, 5,000 milliseconds later, this loop here is awake. It does some processing and goes back to sleep. But meanwhile, even though our main loop here is stopped, it's not doing anything, the processor is still running. It's still processing this. So what we can do is, with this input here, we can have that running off. We can then create other tasks in other header files, say sending MQTT stuff, maybe sending emails, doing whatever else, and they all run essentially independently of this main loop. They can report stuff back up to it, and the main loop can do stuff with that. So the beauty of tasks are that they allow the main event loop to do completely different things, and then the tasks run in the background. So our background task here is it's checking this GPIO for input activity, and it's reporting that to the screen, and meanwhile the main task can be off, la 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 la, jumping around, looking at the daisies, and doing completely different things, yet the two of them are running essentially simultaneous. So that's the power of tasks. The other thing with tasks are you can have them, there are two cores in these devices. You can have the main core run on core 0, and then the tasks, these tasks run on a different core. So they're completely running on separate cores. So if you have something that is very processor intensive that you want to do in the background to your main code, well then you can put it in a task that runs, churns the numbers, and does it away, and it doesn't slow down the main application. Okay, we've covered a lot there in this one. I hope it makes sense. I hope I haven't bored you with all this on it. But we will have a look at tasks, and the next time we'll have a look at an analog task. So what we'll do next is we will take the analog battery one and we'll read that in a separate A to D conversion, and we'll run that in parallel essentially to the GPIO one. Okay, hope that makes sense. Talk to you soon.